Hello. Yeah, so this is it's basically a story of a thing that we've developed. So it's not a lecture, or it's not anything along the lines of hey, you should do it this way. I'm not really here in that capacity. It's more of we've done this and it seemed to work, sort of thing. So please take it for what it is. So it's about this little device. It's called the One Box. It's basically a controller for pumps, motors, similar devices. It's got a bunch of inputs, some outputs, and it talks to a back end. We've developed it for YOW, who are actually a subsidiary of Southeast Water. You might have heard about that company. They're actually the authors of the system. So they've developed the entire, the architecture, the networking side of things. They've developed a prototype for the One Box as well. So our goal at Hydrix was actually to take that prototype and turn it into something that can be manufactured at a cost that has certain quality and that's reliable. So basically, we had a certain challenge in front of us there. So first part of the challenge, cost target. So not being in the ideal world, we cannot throw a Pentium processor into this product and chuck a Linux on it and write a few scripts and off we go. We had to use a microcontroller, and this is kind of roughly what's inside of it. The main part, I suppose, that's relevant to us here is that we've got a 3G modem and network connectivity. And I'm just trying to talk about what the device did. So in this particular picture that you saw just before, it'll monitor level of water in a tank, power, and it'll turn the pump on and off, and it'll report to the back end what's happening. It's got an LED on it, user interface, the simplest user interface there can be. So that's what that is. So that was one part of the challenge. The other part of the challenge was that we had to develop something that I would call high integrity firmware. So that's it's not really safety critical, but if it doesn't work as expected, it does cause unpleasant phone calls. So you basically have to develop it very carefully and think of it almost as if it was a safety critical design. So how did we go about it? Bunch of things. I'll talk about each of these in a moment. So basically, there's a stack of things that we did. I don't know if there are really patterns or behaviors or anything like that. It's just basically, a lot of these are common sense. Some of these might not be. They all seem to work. So looking at this one. So nowadays, a lot of teams use agile development methodologies, Scrum, and so on, which is what we did as well. However, we didn't take that as an excuse to avoid doing a lot of upfront work before hopping into coding. So it's something I would call small design upfront. So going up to the customer or the users and figuring out what the real requirements are, talking to them, asking a lot of impertinent questions about their backend. What's the protocols that you're using? Can we please have a test server? All that sort of stuff. And how is this device meant to work? How reliable do you need it to be? Things like that. Then we broke it down in terms of software architecture. We drew a few whiteboards, drew a few diagrams, discussed things. So we spent a solid amount of work getting that to the point where we actually sure that we understand that we are building, that we understand what needs to be built. A big part of that. So once we're at that point, we've got the software broken down to requirements, features, and even to the point of actually start to think about processes and threads and so on. So first thing I want to talk about is real-time operating systems. They're a good idea. So if okay, we don't have a big operating system. We're working with a little microcontroller, but it's not an Arduino kind of thing. We often do need a real-time operating system, just because the world is inherently parallel, multi-threaded. Everything that's happening around it has processes, and the easiest way to think about software that interacts with it is to also have threads, processes, and so on. So when you think about it, real-time operating systems, they really don't impose any cost, realistically, in terms of licenses or anything like that. There's plenty out there that are basically free. They are cheap in terms of your CPU power and memory. That's probably a few hundred bytes per thread, which is nothing. And most importantly, once you understand how to work with them, they reduce the cognitive load, because instead of having one big loop, one ball of homogeneous piece of software, now you have separate processes that you can reason about, and then you can actually design the interaction between them. Often you would be mapping interfaces to corresponding processes or threads, roughly. Next thing I wanted to talk about, just that, reactor pattern and threads. So now we know we are using the good bedrock of having a solid real-time operating system. We mapped out our design to threads. We designed the event-based interface for them, and we basically use the reactor pattern a lot. If you don't know what it is, Google it, it's useful. Event-driven. So then, when you're actually then checking your design, you can do it on paper a lot of the time. You draw message sequence charts, you make sure it's covering everything that could happen. Very old-fashioned, but it does work, so that was another thing. So these are the actual components, roughly, that we had. We actually had to use a SCADA virtual machine, it's basically an engine for implementing rules, business rules, so to speak. So, if water level is above threshold for that amount of time, then turn on the pump. We wanted to be able, basically, to change this on the fly when the product is in the field. IoT asked us to use a particular virtual machine that's kind of known to them. They can use design tools. The SCADA engineers can actually design these rules without having to know programming languages, or at least textual programming language. They still use graphical programming languages. The other thing that we needed to use was the DMP3 protocol. Many people might not know it. It's quite common in utility industries. So in this case, water industry, it's a messaging protocol, basically, that ensures reliable delivery. It works over TCP/IP, serial port, wire, wet noodle, I don't know. It's basically a self-contained protocol, so we grabbed it as a third-party library and then integrated it. And a few other things that are very common that are going to be pretty much in every type of this device. So configuration interface, so we can talk to it by means other than the protocol. Diagnostics logging, yes. File system for logging things and for storing, the persistent data. Network stack, obviously a bootloader, some drivers, and the real-time operating system. So now I'm going to zoom in on one of these. That's probably the most interesting here, the network stack. That's what it looked like in our case. Mobile devices are fun. So we ended up with a 3G modem. That's probably your only choice these days if you want to have coverage pretty much anywhere. There's nothing else that's as reliable and as accessible as that. We ended up talking to it through a serial port and the TPP protocol. I don't know, has anyone actually worked with the TPP 20 years ago on dial-up? That's the same thing, actually. So good, we understand what that is and we can work with it. Then on top of that, TCP/IP, which I'll talk about. So much fun in these microcontrollers with TCP/IP. And other things, DNS, so that the device can tell, hey, I'm here, this is my current IP address that my network operator gave me at this moment. That DMP3 protocol, and we also run the config interface through there. And this is probably the most important part. I called it network control here. It's basically a piece of software that supervises and manages all of this kind of independently. So I think people probably know what all this is, so I'll zoom in on this one. That's actually what made it somewhat reliable. So with mobile connectivity, unless you're Apple or Samsung and developing one of these, you'll get an embedded OEM modem, a little basically module that you talk to through a serial port. They're less reliable, and you'll have to deal with all of these. So, in the real world, the backend could become offline, the 3G network could be inaccessible, various parts of it. The 3G modem itself might stop working. Our own firmware, some thread could stop working, or anything in between. We had a case when we were developing device early on, testing in the field, and we were basically getting offline and disconnected, and couldn't find out what was going on. So we had to hop into our car, drive on site, and it turned out that there was a truck that used to park next to the pump, blocking the antenna regularly. So it falls, there. So how do we deal with this? Common sense. Number one, we have this process, the network control, to actively actually monitor the network. So we send out a ping, make sure we've got a connection, and other things. Also the low level, the triple P, and even the low level modem comms. If any of this stops working, instead of trying to somehow deal with it, be smart, no, we just restart the whole thing. We shut down the modem physically, turn it off, turn it on, and restart the stack and so on. And finally, there's going to be long outages sometimes. On one of the deployed sites, we get, imagine Easter weekend. It's on Filip Island. I'm just going to be Easter weekend on Filip Island. You do get mobile coverage, but you do not get any data through because it's just far too many people actually using the network. So you get network congestion. So you're offline for hours sometimes. The device, given that it's a controller of something, it's got to keep working even with no network connectivity. So it'll have it'll store its data into a file and then upload it later when it can. So that is very important. So when I talk about, hey, if something breaks, let's shut it down and restart, we use this mechanism, hierarchical state machines. Google them, they're cool if you haven't worked with them. They, once you understand how they work, they allow you to easily work with the real world because they allow you to express ideas as in, if in doubt, start over. Or a bit more about that. You basically can group states, so you can have a state where I'm bringing up the modem and there's steps underneath it, and each step is actually a state. So you can have timeouts and things like that quite easily. So they're cool. If you're developing embedded devices like that, do look into these. They work. In the end, again, you'll end up with less code. They are actually more efficient in that level than flat state machines, and it's easier to reason about them. So you can be very conservative. So let's say I'm sending a command to the modem to do something. I've got a timeout on it, so if it doesn't respond within the expected time, I give up straight away. If it gives me an error code, I do something else. If it gives the expected response in the expected time, I'm good and I can move on to the next state. Things like that. So they're good. Given that this is an embedded device and a lot of things happen in the field somewhere in the middle of nowhere, diagnostic logging is very important to actually bring it up in the world. So please don't read the code. The only point is that the yellow bits, that's all logging. So we basically pretty much log almost everything, even down to the trace level, function, entry points, state machine transitions, any kind of event you can think of. These events then go out through our comms interfaces. So in real time, so when I'm debugging it right now, I've got my laptop plugged into the device. I can get it through serial port, USB, even then remotely, TCP/IP. And even if all of this fails, we store it into a file. So if the device becomes a brick, we can travel in field, grab it, and get the log file of it, and then see what happened. Doesn't happen these days. That only happened very early on during development, during the initial alpha testing. Or occasionally, rarely though, we get a hardware failure, like manufacturing failure, so some component is not soldered properly. Then you can kind of actually deduce that that's what happened from this. Moving on, one of the other things we did was defensive coding. So I already talked about state machines being conservative and having timeouts on everything. This is the other thing. Pretty much any function or method that's got parameters that have ranges and valid and invalid domains, we assert on them. There's about 2,000 asserts in the firmware. And basically, assert means, hey, I don't know what this is. I didn't expect this value, and I don't really know how to deal with this. So in this particular device, it's always better to have a short outage and just reboot the whole thing and start over. Doesn't happen often, but it does mean that basically we never get a firmware bug reported to us, which is good. Hey. Hey. Trick. So it's a valid strategy, but that doesn't mean there are any serious bugs anyway. You can't get too many outages in any case. So yeah. And also we don't have the concept of a production build and a debug build. Like, debug build has all the asserts enabled, production build to be faster has the asserts disabled. No, they're always there, so it remains reliable. Watchdog, very important. So if all else fails, it's a very simple old strategy. So the two cases that happen when a thread stops handling its events for whatever reason, it's stuck, simply stuck, or anything like that. We get a watchdog, or even if the CPU is starved. So basically the lowest priority thread doesn't get enough time to run, even though it's somewhat handling its event but not fast enough, we reboot as well. So very conservative strategy. Again, we don't basically see it, but during initial development, the first month or two when we have 1 or 2 units in the field, yeah, we got these. And now they're there as a fallback in case of hardware failure or anything like that. So talking about coding, coding standard. We picked this one. We're not quite as safety critical as these guys, but the author of that coding standard knows a thing or two about C++. So he's the author of C++. So we followed it, not very closely, as in checking every single line of code, but roughly, I would say. So the interesting points are we're not using exceptions. Exceptions on little embedded microcontrollers don't really add value, given that you've seen all the other strategies that we have for dealing with failure. And we save on memory, and if something is not as expected, we just reboot. So why have exceptions? We don't use recursion for anything, just because it uses memory and there's no particular strong need. And it's actually a common practice in safety critical software, just to not allow recursion. So if anyone's worked in automotive with the MISRA standard, same thing. Slightly more controversial, we actually don't use dynamic heap allocation, so we have no malloc or new or anything like that in our code, except at the very startup when we bring up the threads, just to pre-allocate their memory. The mechanism we use is malloc sometimes, just as a convenience. But once the system is running, we don't ever use that again. So basically what that does, it forces the designers and the developers to think about the exact memory usage 100% of the time, and you pre-allocate everything that you are ever going to need, and then you manually manage memory. So you have your own, say, let's say it's the comms code that needs to send buffers back and forth. It'll have its own pool of buffers and its own hand-coded mechanism for dealing with them. So yeah, it's a bit of work, but then it's customized for every single usage. It ends up being you can control what's happening. We have the stack, when you call a function, parameters, or whatever gets put on the stack, the real-time operating system actually monitors this for us. So our usage of memory is basically 100% managed, visible, and basically very reliable. So finally, this is how we actually develop embedded firmware for microcontrollers at Hydrix. This device uses that framework as well, the common Hydrix embedded framework. It's a framework that allows us to develop apps of this type fairly quickly because we've got all the code that you need all the way up to the application framework. So you're basically left with just writing the code that is specific to that given application. So you already have a framework thing for doing state machines. You just have to define what the state machine is. You have a whole bunch of drivers, so you don't have to read through hundreds of pages of data sheets, which I don't know if you've tried working with some of these microcontrollers. This is actually where most of the work ends up being, because they're complicated things. They're very power efficient and they have high performance, but they take a lot of time to actually learn how to work with them. We have real-time operating system abstraction, we have a build system, we have documentation, we have reference electronics design. Again, we can crank out a new device of this type fairly quickly. Don't have to research, don't have to bring in electronics component libraries into our CAD system, anything like that. We just customize the reference design for our thing and off we go. We've done many products with this framework. Some of them are medical devices. We've been basically using it for some years and gradually improving it, and we will continue improving it. So there's our plug. So if you have a need for this type of device, something with a microcontroller that's reliable, talk to us. All right, so yes, of course, nothing is ever perfect. This device, although somewhat small, was quite a journey for us when we went through it. So 3G modems, yay. So, they work, but good. The thing is, if you're not, again, as I said before, if you're not doing one of these, and if you're not up to that scale, you're forced to buy one of these OEM modules. So you go look in the marketing documentation. Good, it's all there, all the features are listed. Then you look at the real documentation after you sign all the NDAs. How do I do this? Some things are not always documented. And then you eventually grab the device and work with it, and you find out that it doesn't always work as expected. So it took us a lot of effort to bring it up. I actually do have to give a credit to our supplier. So they're not the manufacturer. Not going to name names for the manufacturer. They're probably all similar. But these guys are pretty good. So again, if you're looking for a modem or embedded type modem, basically, they've helped quite a lot. Yeah, TCP/IP on microcontrollers. So the first one, maybe let's just use the TCP/IP stack that's in the modem. It's all there. It's all in the marketing materials. No. We wanted to open more than one socket at a time, and that's just too much for it. So, so then we switched to a proprietary closed source TCP/IP stack that came with a good pedigree from a pretty reputable company. So we thought it's a good bet. Okay, we have to give up on this modem. Let's get this thing. It costs a lot of money. Same story. No proper documentation in the end. After some weeks of testing, it turned out to be unreliable and very hard to work with. So, a few months down the line, we ended up with just porting lightweight IP, and that works. So there's a lesson there. Lightweight IP, pretty good. And even if it did have an issue, which we actually didn't find any, but if it did have one, you've got the source, so you can go in and fix it. I remember putting in a firewall in it, just coding it up. So try doing that with a closed source thing. File systems, same story. So reputable third party, big company, closed source, binary, flash file system, nice library, didn't work. Didn't pass the stress testing. You're basically stress testing you run for a couple of days just reading and writing to it, and eventually it would, you write something and it reads back something else without telling you that that's what happened. Yeah, can't use that. So again, we ended up with YOW's, pretty well-known flash file system works. So I think there's a pattern emerging, So basically, paying lots of money for something is not a guarantee of success every time. So in the end, these are the things we've done. It worked for us. We've got thousands of these in the field now, and the production continues. There's going to be more of them. It delivers a lot of direct financial value to IoT. We actually don't have reported firmware issues, and this is not because of all the watchdog resets that we put in. I think we've just spent a lot of time, a lot of effort, and a lot of time testing it up front. So it's a very solid piece of firmware, even though I say so myself. So thank you. That's all I had at this stage.